Thank you to AnyDesk for supporting PBS. To observe the quantum nature of gravity and of spacetime itself, we need a particle collider the size of the solar system. Or we could just physics smarter and build one on a lab bench. Here's how. Hey everyone, before we start, we need your help. The algorithm is hiding episodes from subscribers. From past experiments, which many of you participated in, we know that the best way to help is to like the episode and to leave a comment. That tells the algorithm to share it with more of the community. And if you haven't yet, subscribe and hit the bell so you don't miss new episodes. You're an amazing community and we want to keep delivering great content to everyone, so thanks for your help. Now, on to the episode. The quantum world is certainly strange. Objects in multiple places and states at once, random transitions between states and places, weird instantaneous communication over large distances, all that good quantum weirdness. But perhaps the strangest thing about quantum mechanics is that its rules seem so different from the classical large-scale world, and yet the latter comes from the former. But how? And at what size does that happen? A related mystery is the connection between gravity and the quantum. Gravity seems more in line with the classical world. It is crisply defined and very non-random, but gravity is the fabric of space-time, which is knit together on scales far smaller than the quantum. So, at what point does space-time itself become quantum? The question of the quantum classical transition and the related quantum gravity connection are notoriously difficult to probe directly due to the challenge of accessing the minuscule quantum world and the minusculer quantum gravity world. But maybe the answer is not to build tiny experiments or giant colliders, but to make the quantum world big enough to meet gravity and the classical world halfway, perhaps inside a regular laboratory. The known laws of physics can be pretty clearly broken up into these two realms, those describing the large-scale classical world and the tiny quantum world. Classical physics works great above about a micrometer, where objects are made of many, many atoms. Everything larger is, as we say, macroscopic. Quantum mechanics rules below the nanometer scale, at single molecules and atoms and smaller. But the in-between scale, the mesoscale, feels both of these worlds. It is, as we say, semi-classical, behaving mostly classically in some ways, but exhibiting quantum effects in certain conditions and when carefully coaxed. Today, we're going to look at approaches and some example experiments for probing fundamental questions by looking at this intermediate space where both classical and quantum mechanics are at play. Maybe we don't have to wait for that solar system-sized particle accelerator to do this cool stuff. We'll look at two paths. One is to look for a breakdown in our classical understanding of gravity at the mesoscale. The second will be to look for true quantum effects in as large a system as possible, but also in the mesoscale. So we're going to try to make gravity small and then make quantum big. If we can get them to meet somewhere in the middle, maybe we can even make gravity quantum. Let's start with an experiment so elegant and simple that it's been our go-to for measuring the strength of gravity since we, first tried to measure the strength of gravity. When Newton first wrote down his law of universal gravitation, he reasoned his way to the proportionalities based on a falling apple and the orbit of the moon. The force of gravity had to be proportional to the product of those masses divided by the square of their separation. But he had no idea of the value of the constant of proportionality, the gravitational constant. For that, he would have needed to know the Earth's mass. But how do you weigh the Earth? The answer is that you first measure g with known masses and then work your way back to the planet. But that requires us to measure the minuscule gravitational attraction between masses that we can make and then weigh. And it wasn't for another century after Newton's law that this became remotely possible. The guy who did it should have been John Michell, the most underrated of the geniuses of physics. This is the same guy who first conceived of the Newtonian version of the black hole, the dark star. Mitchell's idea was to measure the minuscule gravitational pull between a pair of metal spheres using a remarkable device, the torsion pendulum. This cunning device suspends a rod on a thin wire. Rotating the rod twists the wire, leading to a restoring force that pulls it back. This can produce pendulum-like oscillations, but it can also be used to measure the strength of the force doing the initial displacement. The restoring force increases with twist, so more twist means more force. And the torsion pendulum is almost completely free from friction. With a thin wire, it can be sensitive to extremely tiny forces, perfect for the minuscule gravitational force exerted between non-planet-sized objects. Mitchell actually built his torsion pendulum, but he died before he could complete the experiment. His close friend, Henry Cavendish, inherited the device, refined the design, and saw the experiment through. It looked something like this. 2 lead balls of around a kilo were fixed to the arms of the pendulum, while a pair of 160 kilogram balls were fixed near these two, with the intention of them gravitationally attracting the smaller balls. The amount of twist in the pendulum would measure that force, and because all the masses and distances were known, the gravitational constant should fall out as the last unknown in the equation. The experimental design and the care taken were extraordinary, so much so that in 1798 Cavendish measured the gravitational constant to within 1% of the best modern value. Fun side fact, Cavendish described his experiment as weighing the Earth, because with G in hand, we could now calculate the Earth's actual mass just from the gravitational acceleration at the surface. In the 225 plus years since Cavendish's measurement, this experiment has been greatly refined, but we've improved on that first measurement only by about 1 more decimal place because Cavendish and Mitchell did such a good job. However, we're also now able to do this experiment with much smaller masses, perhaps even small enough to see if the rules change as we approach the quantum realm. And there are some reasons to think they might. In a previous episode, we talked about how gravity might deviate from the Newtonian inverse square law at very short distances, if there are extra coiled up dimensions on those scales. Essentially, gravity leaks into those dimensions very close to the source, causing it to weaken faster. But at longer ranges, it settles into the regular inverse square fading. But there are other reasons to think that gravity might behave this way. In string theory, there are ways for gravity to behave like the quantum forces, whose coupling strength changes with distance due to self-shielding. There's also the hypothetical chameleon field, which is a dark energy candidate that has a distance-dependent variable mass that could do something similar. And give a theorist enough chalk and a sabbatical, I'm sure that they'll come up with several more options. But how to test? The problem is, performing a Cavendish-type experiment with quantum or even mesoscopic masses brings with it a new slew of noise and possible interfering effects that not even Cavendish's dedication to precision could overcome. For starters, we know the gravitational force is absurdly weak between 2 small masses when compared to the other forces of nature. For example, the gravitational attraction between 2 electrons is about 42 orders of magnitude weaker than the repulsive electromagnetic force pushing them apart, making it essentially impossible to measure gravity in that case. We can use neutral masses, but even those tend to have internal electric charge distributions that can lead to dipole interactions when objects are close by. And when surfaces get very close, the Casimir force and the van der Waals force come into play, typically with much greater strength than gravity. Even if we could compensate or outright avoid these effects, there are many other potential sources of noise. Natural vibrations in the experimental setup, seismic noise, and even gravitational noise from nearby massive objects. A recent example of a successful, teensy-tiny Cavendish experiment came from a group of physicists in Vienna. They built a Cavendish setup with tiny gold spheres 1,000 times lighter than the original lead source mass, at under 100 milligrams. These 2mm gold beads capped a pendulum rod suspended on a wispy silica thread. this experiment was all about minimizing external noise and interference. As with typical modern Cavendish experiments, this one was conducted in a high vacuum, and the masses were carefully discharged, here using ionized nitrogen. A conductive Faraday shield between test and source ensured no electromagnetic interactions between the balls. The tiny gravitational field they were trying to measure between the balls, which were separated by about 2.5 millimeters, was no stronger than that of a grad student standing 2.5 meters away, or a Viennese tram rumbling by on the street outside. To help quieten the gravitational noise, the experiments were done mostly between midnight and 5 AM during the quiet Christmas season, and I guess grad students were positioned strategically and asked to remain motionless, on top of asking them to stay up all night and to miss the holiday. Even with these precautions, more cleverness was needed to make the measurement. Now, Henry Cavendish directly measured his displacement of the torsion pendulum arms by seeing how far they moved. But in this and other modern Cavendish experiments, researchers have a way to massively amplify that signal. They oscillate the position of the source mass, so the test mass experiences a varying gravitational field. The pendulum also oscillates, and the varying gravitational field will very slightly perturb that oscillation. This allows a direct measurement of the gravitational acceleration caused by the source mass. The benefit of this method is that the researchers can watch for long periods of time as the tiny perturbations build up. By integrating the signal for, say, half a day, they can detect a gravitational acceleration of 10 to the power of minus 10 meters per second squared. That's 100 billion times smaller than what we feel at Earth's surface. The gravitational constant measured in this experiment turned out to be consistent with the known gravitational constant as measured by Cavendish and later experiments. There was a difference of around 9%, but that's within the experimental uncertainty of this setup. So the laws of gravity may not be too different for these sub-100 milligram masses, but since the gold balls used here are more comparable to a baseball in size than to an atom, that may not be too surprising. It's impossible to know exactly how small we need to go to see if the strength of gravity changes, if it even does. But this team feels that it should at least be possible to get down to the Planck mass, nearly 10,000 times smaller than the current experiment, with several significant but plausible refinements of the methods. If we wanted to get these experiments down to truly quantum scales, then we need to go down another 9 to 12 orders of magnitude. That may not be possible with the Casimir setup, but other approaches like levitating nanoparticles or cryogenic suspension may make it possible. So, we've been talking about measuring gravity down to the near quantum scale. The other way we can go is try to observe quantum effects on as large a scale as possible. One of the most defining of quantum phenomena is quantum entanglement, in which a pair of quantum objects can become correlated with each other in a way that defies classical explanation. We typically think of entanglement as existing between truly quantum scale entities. For example, a pair of electrons may have entangled spins, each spin direction undefined when taken as separately, but those entangled spins are defined relative to each other, for example, as having opposite directions. Entanglement should exist between large systems, but the larger the system, the harder it is to observe. The correlations between individual particles can be smeared out and lost to the surrounding environment in a process called decoherence. Decoherence plays a huge role, perhaps the entire role, in making the quantum classical. And we could understand that process a lot better if we could somehow observe entanglement in a macroscopic property of a macroscopic system. One of the most promising approaches is in the field of optomechanics. Imagine a laser light bouncing between two mirrors. We call this an optomechanical cavity. The mirrors, in this case, are suspended so they can oscillate forward and back. A photon from the laser hitting the mirrors will transfer momentum that depends on the photon frequency. That sets up an oscillation in the mirrors, which in turn changes the size of the cavity, which in turn changes the frequency of the modes of light in the cavity. This leads to a feedback cycle in which the oscillation of the mirrors is correlated with the frequency of the photons, and done carefully enough, this correlation can be a true quantum entanglement. This has been achieved with very, very tiny mirrors. The first was in 2010 with an entanglement demonstrator between a light field and just a single membrane of silicon nitride as the mirror. But in 2011, a pair of mirrors was put into entanglement, not just with the bouncing photons, but also with each other. That means two macroscopic systems in a state of entanglement with each other. So here we are really blurring the line between the quantum and the classical. But these mirrors were still tiny, really mesoscopic. It would be nice if we could achieve the same result for something truly macroscopic. Of course, it would be incredibly expensive to build a much larger optomechanical cavity with all the precision engineering, the noise mitigation tech, etc., to even attempt a macroscopic optomechanical entanglement measurement. Good thing we already built one. The Laser Interferometer Gravitational Wave Observatory, LIGO, was designed to detect space-time ripples, but in principle could be used to detect correlations in the oscillations of the mirrors that point to true entanglement between these genuinely macroscopic objects. Many of the challenges for doing this with LIGO have already been solved. In order to detect actual gravitational waves, incredible work was done to minimize random noise, to flag and remove seismic vibrations, and even remove spurious gravitational signals. The major outstanding challenge is dealing with a special type of noise that can confuse the entanglement signal. This is non-Markovian noise, which, unlike regular noise, develops correlations over time, sort of like a memory, that can be confused for the entanglement source correlations. Motivated by the goal of teasing out any signs of entanglement in LIGO, in 2024, a group of researchers went back through the LIGO's data, now equipped with new and improved models to account for the non-Markovian noise. And they haven't found anything yet. But with better noise modeling and more integration time, we may spot the quantum whisper of entanglement between LIGO's 40-kilogram mirrors, which span its 4-kilometer arms. Detecting entanglement between classical or semi-classical objects can help us understand the boundary between the quantum and the classical. The Cavendish experiment we started with was about exploring the quantum nature of gravity. Now, the Holy Grail would be to bring these goals together to detect entanglement between systems in which the entanglement is actually mediated by gravity. If gravity can do this, it means that gravity itself must have quantum properties. Now, we did look at one approach a while back with a Stern-Gerlach type experiment in which nanodiamonds in a superposition of positions nudge at each other gravitationally and so become quantum entangled. But there are other proposals that don't require the superposition of positions. For example, putting test masses in a superposition of spin states whose energy difference then leads to a difference in the gravitational fields that they generate. Or even a real Cavendish-like experiment in which a pair of oscillating pendula develop non-classical correlations over long periods of time that can only have arisen from a gravitationally mediated quantum connection. All of these ideas are still in early phases, from thought experiment to active planning. The technological hurdles are major, but the crazy thing is that the hurdles are just technological, and there are clear paths to solving them. This is what's so cool. We will soon have a lab bench experiment that can start to map the quantum classical divide and even observe the quantum behavior of gravity. Physics is cool. Just a couple hundred years from lead balls suspended from wires to the quantum nature of spacetime. Thank you to AnyDesk for supporting PBS. AnyDesk was created because whether you're in a remote location or just working from home, the need for reliable, secure communication and data transfer remains important. With AnyDesk, secure direct file transfer bypasses the cloud entirely, allowing you to move large media files, benchmarks, logs, or firmware updates between systems. And if you're working on servers or older systems with remote server monitoring and CMS access, you can control dashboards and monitor web servers directly from your phone or tablet. Plus, it's available across all major platforms and has backwards compatibility with older systems in case your data is running from legacy systems. AnyDesk is available for personal use, but if your research requires a lot of global coordination, AnyDesk offers custom-tailored business plans. To learn more about AnyDesk, go to anydesk.com/spacetime or check out the link in the description.